Hey, what's up, everyone? Today we're going to be finishing off States of Matter by doing some practice. And so we're going to go over the 2013 local test and the 2012 national test. I'm sorry that these are like older tests, but I end up using a lot of the problems from like the newer tests in the lesson, so I kind of have to use these. But I guess you got to do what you got to do. So let's take a look at problem 13. A sample of an ideal gas has a volume of zero point 0.5 liters at 25 degrees Celsius and 1.20 atmospheres of pressure. What is its volume at 75 degrees Celsius and 3.60 atmospheres? So let's write down the PV equals nRT values. So we know that the pressure is 1.20. We know that the volume is 0.5. We don't know N. We know that R is going to be 0.08206. And we know temperature is going to be 298, which is 298 Kelvin, which is 25 degrees Celsius. And so now let's solve for N. So N is going to be 1.2 times 0.5 all over 0.08206 times 298. So N is going to be about 0.0245. And so if we look at what the question is asking for, what is its volume at 75 degrees Celsius and 3.60 atmospheres? Well, the volume is, we don't know. And the pressure is 3.60 equals N, which is 0.0245, since we're not changing the number of moles. And then R is going to be 0.08206. Temperature is going to be 75 plus 273, which is 348. So now if we just take all these values and we just dump them into a calculator, which I'm going to do right now, 0.08206 times 348 divided by 3.6, you're going to get that volume is 0.195. And that is answer choice B. And we are correct. So again, just using PV equals nRT to find the number of moles, and then taking that and applying it to the next set of conditions. Let's move on. Problem 14. In a mixture of nitrogen and oxygen gases, the mole fraction of nitrogen is found to be 0.7. The total pressure of the mixture is 1.42 atmospheres. What is the partial pressure of oxygen in the mixture? Okay, so remember that pressure and the number of moles are going to be related. So the partial pressure of a gas is going to be related to the mole fraction of the gas. And that is because pressure is directly involved with the number of moles that you have. So as you increase the number of moles, you're also going to increase the pressure. So that means if you take the number of moles of 1 over the total number of moles, that's going to equal to the partial pressure of 1 over the total pressure. So if we're told that the mole fraction of N2 is 0.7, that means the partial pressure of N2 is going to be 0.7. And since we know that the total pressure is 1.42 and the partial pressure of nitrogen is 0.7, that means that the partial pressure of nitrogen is going to be 0.994. My bad about that. And so if we're trying to find the partial pressure of oxygen, we just take the total pressure, 1.42, and subtract that value, 0.994. And that is going to get us 0.426, which is answer choice B, which apparently I had on the screen this whole time. Whatever. So again, the important relationship is this, that the mole fraction is going to be the same as the partial pressure. Let's move on to problem 15. The substances below have molar masses that are the same within plus or minus 2 grams per mole. Which substance has the lowest boiling point? This part here is important because it tells us that the London dispersion forces are going to be the same. So now we have to look at the other intermolecular forces. If you look at B, C, and D, well, you know for a fact that C is going to have hydrogen bonding because of that OH. So hydrogen bonding. And if you draw the diagram for B and D rather, you're going to see that these are going to be dipoles. So you're going to have dipole-dipole forces in these. And these are in addition to the London dispersion forces that they're already facing. And so the one that has only London dispersion forces, LDFs, is going to be A. And if A is the only one that has exclusively London dispersion forces, it has the least intermolecular forces and therefore the lowest boiling point. So the answer is going to be A. And we are correct. Let's go on to problem 16. Which statement is correct about the critical point of a phase diagram? Okay, remember what a phase diagram looks like. It's going to be in this form, and the critical point is going to be right here. And the critical point is like the intersection between these this liquid and a gas, and it's at like a super high temperature, super high pressure that makes it have really weird properties. So remember, pressure is going to be on this axis, and the temperature is going to be on that axis. So let's go through the answer choices. Solid, liquid, and gas are present in equilibrium. That's not true. The thing that they're referring to here is the triple point, which is found right here. That's called the triple point, and so it can be A. B, liquid and vapor are indistinguishable from one another. That is true. At the triple point, they're at this weird phase where it's like liquid and vapor can exist at the same time, but it's super high temperature and super high pressure. So yeah, B makes sense. Let's take a look at C. Liquid can be produced by a change in pressure. Remember, liquids are going to be here. Here's going to be your gases, and here's going to be your solids. So if you were to change pressure, you can't get past these temperatures, or rather past these pressures, you're going to have supercritical fluid. These are not going to be your standard liquids, so no, by a change in pressure, you cannot produce liquids. Vapor can be produced by a change in temperature. If you decrease or increase the temperature, let's say you decrease it, you're going to end up in this liquid form. If you increase it, you're going to end up in the supercritical fluid form. So no, you cannot produce vapor by changing the temperature, meaning the only answer choice that makes sense is B. And we are correct. Okay, let's take a look at the next one. When equal volumes of the following pairs of liquids are mixed thoroughly and allowed to stand, which pair is most likely to separate into two layers? Well, what you need to know about this is that like dissolves like. So polar, it dissolves polar, nonpolar dissolves nonpolar. But when you put polar and nonpolar together, they're going to separate into two layers. It's like, water and oil. And so which one of these are going to have, two different types? Ethanol and methanol, these are both polar. And so they are going to dissolve. So it can be A. Carbon tetrachloride and methanol. Carbon tetrachloride is nonpolar and methanol is going to be polar. And so yeah, these are going to separate into two layers. But let's take a look at the other ones. Hexane and pentane. Hexane and pentane are both nonpolar, and so they are going to dissolve each other. And then same thing with carbon tetrachloride and hexane. These are both nonpolar, and so they are going to dissolve each other. Therefore, only B makes sense, and therefore B is the right answer. Let's move on to the last question of the local exam. For the same atoms at the lattice points, which lattice exhibits the lowest density? So remember, if you remember back to your common lattice, the unit cells, the ones that's gonna provide the lowest density is gonna be your simple cubic one. It's gonna be about, I think, 52% empty space. Basically, it's just like a cube, and all you have are 8 atoms at the corners, and so a lot of space is wasted, and it's gonna be one of your most inefficient ones, and therefore it's going to have the lowest density. And we are correct. Let's move on to the national exam. Problem 13. At the molecular level, the factor that determines whether a substance will be a solid, liquid, or gas is the balance between. Well, remember, these are going to be, one of the most important ones is going to be intermolecular forces, not intramolecular forces, so we can get rid of those. Intermolecular forces are going to explain how they're going to interact with each other. And so intermolecular forces are very important. And the next bit is kinetic energy or potential energy. Well, kinetic energy is going to be more important. Because remember, kinetic energy tells us how fast and how much these molecules are moving. So remember, in solids, they're not moving too much. In liquids, they're moving a little. And then in gas, they're moving a lot. So the change in kinetic energy and the combination of their intermolecular forces are going to tell us whether a substance will be a solid, liquid, or a gas. And so the answer is going to be A. And we are correct. Let's move on to question 14. A gas sample in a flexible container is maintained at constant pressure while its temperature is increased from 25 degrees Celsius to 75 degrees Celsius. If the initial volume of the gas is 4.2 liters, what is the change in volume due to the temperature increase? Remember, volume is proportional to temperature, and I think this one is Charles' law. But the temperature here is going to be absolute temperature, so temperature in Kelvin. So if we are 25 degrees Celsius is going to be 273, and then 75 degrees Celsius is going to be 323 degrees Celsius. Okay, that looks right. Um, and so what this tells us is that since the volume is being increased by a factor of 323 over 273, then that means the volume is also going to be changed by a factor of that. So if we're trying to calculate the new volume, we would just multiply this factor by the initial volume. And if we do that, we're going to get 323 divided by 273 times 4.2. And if we just take that number, and since we're trying to find the change, if we just subtract 4.2 from it, we are going to get that it's about 0.7. It's about 0.7, which is answer choice A. And that is correct. All right, problem 15. The critical temperature of carbon dioxide is 304.3 Kelvin. Which statement is true about the behavior of carbon dioxide above this temperature? So remember, above this temperature, let me just draw this phase chart again. Critical point here. Above this temperature, you have your supercritical fluid. And so let's see which answer choice makes the most sense. A, solid, liquid, and gaseous carbon dioxide are in equilibrium above this temperature. That does not make sense. The only time that they're in equilibrium are going to be at the triple point here. So A does not make sense. Liquid and gaseous carbon dioxide are in equilibrium above this temperature. This is not really true. They exist in this like limbo form. So they're not in equilibrium. Instead, they're like in a kind of almost new phase on its own. C, liquid carbon dioxide does not exist above this temperature. This is true. What exists above this temperature is going to be the supercritical fluid. This is not liquid carbon dioxide. It's like a mixture of liquid and gaseous carbon dioxide. And D, carbon dioxide does not exist above this temperature. That does not make sense. It does. It's just in a weird form. And so C is the only one that makes sense. And so that's the answer. Let's move on to question 16. Which substance is matched incorrectly with the type of solid that it forms? And so let's go through it. Ammonium sulfate, these are ions, and when they come together, they are going to create an ionic solid. So it can be A. B, metallic solid. Lead is a metal, and it is going to have metallic bonding, so it is a metallic solid. Potassium chloride, again, these are ions, and when they come together, they create an ionic solid, so that can't be true. Silicon dioxide, though, if you remember, silicon dioxide was one of those specific examples of network covalent solids. And so these are not molecular solids. These are network covalent solids that are held together by covalent bonds. And so this is not matched correctly to the type of solid it forms. The answer is D. And we're correct. Second to last, metallic sodium has a body-centered cubic unit cell. How many atoms are contained in one unit cell? This is almost trivial, but you can just draw out the diagram too. So a body-centered cubic is going to have those 8 atoms at the edges, and let me just draw them, and then a 1 at the center. So the 1 at the center counts for a whole atom, and then you have 8 1/8 atoms. I think my cursor was there the whole time. And so the total amount of atoms that you're going to have is 2, which is answer choice B. And we are correct. Let's go on to the last one. Which substance has the lowest boiling point? You might be tempted to go with H2O because it's going to have the least London dispersion forces since it's the smallest. But remember, water has those hydrogen bonds. And so they're going to be pretty strongly put together. So it's not going to have a low boiling point. And now, since the dominant forces in all of these are going to be your London dispersion forces, it can't be B or C because it's going to have more London dispersion forces than H2S since they're going to be bigger than H2S. So our answer is going to be B, which is H2S. I hope you learned something. That's all I have for this lesson. And we have finished Unit 3, which is states of matter. And I'll see you later.